Let's talk about vector equations of lines. Now the lines that we're used to the equation y equals mx plus b. We're used to that being the slope and the b being the y-intercept. And we think about that as slope, a point and the slope sort of define a line. Or 2 points define a line. Well, it's still a point and a slope because the 2 points define the slope, and then we just need one of those points plus that slope. A point and a slope define a line. But we want to talk about this in terms of vector. So let's start off with 2 dimensions then, and we'll start by thinking about this as an example. In 2D, we want a line that goes through the point 1, 2. Notice the brackets are round, so that's a point, and is parallel to the vector 3, 4. That's a vector. So let's check this out then. And I'll just write here so I can draw. Let's use the black one. So here's our xy. Now 1, 2, 3, 1, 2, 3, 4. That's supposed to be straight. There's that vector 3, 4. So the line is supposed to be parallel to that. And it's supposed to go through the point 1, 2. So it goes through that point 1, 2 and it's parallel. So I'm going to change color here so we can see the line. How about green? So it's all of we're talking about everything on that line, everything on that green line, every point there is. Now how do I get to that any point? Let's say how do I get to this point? Well, if I think about it, I'm going to take, I get to use all the colors. To get to this point, all I need to do is start at 0, 0, go to the point I want to get to, that's the point 1, 2, and then now I'm on the line, but I'm not over here. But I can move along the line by just taking multiples of this point 3, 4. So if that blue vector is the point 1, 2, if I take the vector 1, 2 and I add to it, let's say one of these vector 3, 4s, I'll get the point 4, 6. So 1, 2 plus 3, 4 is 4, 6. So that's on the line. So if I wanted to get a point, let's say that was way up here, well, maybe I'll take 2 of those 3, 4 vectors, or 1.5 of those 3, 4 vectors. If I wanted to get a point that's down here, maybe I'd go up 1, 2, and then minus one of those 3, 4 vectors. So what I'm saying is I go out to the point 1, 2 and then either take a positive multiple of 3, 4 or a negative multiple of 3, 4, but there's some scalar multiple. So I'm going to put that in there, k, and that gives me, I'm going to say r, any point on the line. So now I've expressed all the points, r, they're xy points, as vector 1, 2, that gets us on the line, and then the direction vector, this 3, 4 is going to be we're going to call that to be our direction vector. This 1, 2 is going to be our point on the line. So let's go back here. So we have a point on the line, x naught, y naught, and a direction vector d, that's the 3, 4, the d. So if I want to write this in escape. We'd say that that's r. I'm just using r as the vector for the line. It's a vector equation of the line. Is equal to our point. So I'm going to call that r naught. Again, that should be a vector because I want to, so I'm going to put a hat on it. Plus k times the direction vector. So there's our vector equation of a line. We have the slope. The slope's represented by the d, the direction vector, and we have the point. The point's the r naught. Pick a different k, get a different point on the line. Yeah, you're picking one value. You're picking a k value. So it's a one-dimensional object. Yeah, a line is a one-dimensional object. Now in 3D, it says here repeat in 3D. I could just copy this down and paste it and go boom, done, 3D. And then you might say you didn't do anything. Well, now it's 3D. So our r naught, our point, our initial point then, is going to be equal to an x and a y and a z. So it's in 3D. These should have like valid. So I'm making them subscript with the 0 just to say that they're set numbers. That's the point that the line goes through. And likewise, when I talk about a direction vector, I'm talking about a three-dimensional direction vector. So there's a D1, a D2, and a D3. Now it's in 3D. In 4D, you know where we're going with this. I'm going to add like a W here and a D4. So this vector equation of a line works in any dimension. 2-dimension is how we drew it, but we can see it in 3-dimension. In 3-dimension, we think of it as like a string going through 3-dimensional space. The direction vector D is parallel to the string, and this R naught, the X naught, Y naught, Z naught point is a point on the string. You start at the origin, go to the string, and then go, so many K is the so many multiples either forward in the direction vector or negative in the direction vector, and you'll get all the points on the line. There's our vector equation of a line. To get it, all we need is a point on the line, any point on the line, and a direction vector, any vector parallel to the line. Still a one-dimensional object, but here it is embedded in 3-dimensional space. So we have the vector equation of a line. Let's just use this in an example. I want to find the equation of a line that goes through those 2 points. Okay, what do I need for equation of a line? I need a point. Okay, I've got 2 of them. I only need 1. And I need the direction vector. So let's get the direction vector first. The direction vector for our line in question can be the vector that joins these 2 points. So the x value goes up by 8, the y value goes up by 1, and the z value goes down by 2. So there's the direction vector. That's the point that starts at the point 1, 0, 2 and ends at the point 9, 1, 0. There's our direction vector. So now if I want the equation of our line, that's just going to be, we have our point on the line. I could choose either of them. I'm choosing the first one arbitrarily just because it's the first one, and our direction vector. And yes, any direction vector, any vector that's parallel to this will do as well. So you could make this direction vector a unit vector if you want to, but you don't have to. So now we found an equation, the vector equation of a line that goes through those 2 points, 3 dimensions. Now, more questions. Find the equation of the line that goes through the origin and is perpendicular to those 2 vectors. Oh, okay. So I'm going to get I lose my pencil. Here it is. My Sharpie and my pencil. So there's one vector, there's another vector. What I want is, I want the line to be perpendicular to these 2 vectors. Okay, let's set back for a minute. What do I need for equation of a line? I need a point, goes to the origin, 0, 0, 0. So we've got that point. And I need a direction vector. The line is supposed to be perpendicular to those 2 vectors. So the direction vector that I'm talking about is the vector perpendicular to those 2 vectors. How do I get a vector perpendicular to two vectors, I'm going to cross product them. I'm going to cross product 1, 0, 1 against 0, 1, 1, and I'll get a vector perpendicular to them. So that's the first thing I'm going to do. So again, why do I know that I need to do that? Because I need a direction vector and I need a point. So the direction vector is going to be equal to these two vectors cross product. Doesn't matter the order that we cross product them in. If I would have switched those around, I just would have got a negative. It still would have been a valid direction vector. We need any vector of any size that's perpendicular to them. So let's take our cross product then. I'm going to have, now there's that big formula, or you could do the determinant one, but I got 0 and minus 1. Now remember that the middle component has a negative of the formula. That's going to be 1 and 0, so negative 1. And 1. All right. Did I do this correctly? Well, let's see. Is this vector perpendicular? Let's dot product 0, 1, 1 with our direction vector. That's going to be 0 minus 1 plus 1. That equals 0. So it is perpendicular to this vector. What about this 1, 0, 1? Minus 1 plus 0. Yeah, okay, so there's our direction vector. And we have our point. So I'm going to write my, I'm going to write the equation, the vector equation of a line, which is just a way of expressing the point and the line and a slope. Point and a slope. Still point and a slope. You might have written it without the 0, 0, 0. Yeah, that's okay. I like writing the 0, 0, 0 in there because it makes it look like all the other patterns. It's a point and a slope. Okay. Point and a slope. We know one way to express a line. There's going to be three ways. So the first way is the way we've been answering these questions up till now. Our vector equation of a line. The R is all the points on the line. R naught is at least is 1 point on the line. T, or we could use it as K, is our that's our one-dimensional. We get to pick any value for that to plug in to get any point on the line, and D is our direction vector. So here's our vector equation of a line, the one that we've been working with. It's really just telling you two pieces of information. Here's a point on the line, here's the vector that's parallel to the line, and it's putting them together. The parametric equation, well, instead of writing it all, like take a look at our line from, through the origin perpendicular to those two vectors. The x value is 0 minus the k value. The y value, the y component of every point on the line, is 0 minus the k value. The z is 0 plus the k value. So there I'm just expressing the x and the y and the z separately. That's what parametric is. The x, the point that the line goes through is x naught, y naught, z naught. The direction vector is d1, d2, d3. So I'm just expressing each component with the t parameter, our one-dimensional parameter. It's the same information. Here I read off a point on the line, r naught. Here I read off the same point on the line, x naught, y naught, z naught. I can see the direction vector is the d here. Here the direction vector is just written as d1, d2, d3 in components. Symmetric. Okay, this is sort of a weirder one. It has the same information, the x naught and the d1. So here's the x naught and the d1. It's equal to y minus y naught over d2 and z minus z naught over d3. So here's the symmetric way. how do I get from the, I can see how to get from the vector to the parametric or back and forth. How do I get to the symmetric? You get to the symmetric by taking each one of these parametric equations and solving it for t. So if I solve this top equation for t, the x naught would come over, it would be x minus x naught divided by d1. If I solve each one of these equations for t, then they're all equal to t, so here I set them all equal to each other. It's like I eliminated that t parameter. I can still see the two pieces of information though for the line. If I write an equation like this, I can still read off the x naught, y naught, z naught as the point, and the denominators, the d1, d2, d3 as the vector. So there's just three different ways to write this and to write a line, and all three ways are just presenting those two pieces of information. Now, there's a little wrinkle that I haven't mentioned yet, and that's what if one of these d's is 0, because then I don't divide by 0. So before we talk about here, you can see this peeking out, what is the intersection of a line. Let's just do an example. So I'm gonna write down the equation of let's write down a parametric equation of a line. So to define a line, I just need to tell you the point it goes through. I'm gonna be super unimaginative and say it goes through the point 1, 2, 3, and now I need a direction vector. I'm going to say the direction vector is 4, 5, 6. Terrible, not imaginative at all, but there it is. And I guess for T4, usually we would write it as 4 times T, so let me just move that over. So I just made up this line. I can see the point that it goes through, 1, 2, 3. I can see the direction vector, 4, 5, 6. So if I wanted to write this given in parametric form, if I wanted to write it in vector form, then I just have to write it as r is equal to the point, which is 1, 2, 3, plus the parameter times the direction vector, 4, 5, 6. Okay, so now it's easy to go from parametric to vector, or vector to parametric. Let's do that symmetric one now. So for symmetric, it's going to be x minus 1 divided by 4 is equal to y minus 2 divided by 5 is equal to z minus 3 divided by 6. And how do I know it goes through the point 1, 2, 3? If I make x equal to 1, this fraction equals 0. If I make y equal to 2, this fraction equals 0. Z equals to 3, this fraction equals to 0. So the point satisfies that symmetric equation. And I can see its direction vector here as the 4, 5, 6. All right, so switching from one form to another, not bad. Let's do another example, but in this next example, I'm going to give you the vector equation of a line. I'm going to take this same equation, but I'm going to change it to be 4, 5, 0. And I'm going to say, here's a vector equation of a line. What's the symmetric equation? Now, the only thing I changed was this D3. So all of this should be the same, except instead of 6, it's a 0. Now I see the problem. When one of these direction vector pieces is 0, I end up dividing by 0. What do? What you do is, this formula doesn't make any sense. Divide by 0 unless the top is 0. So you represent that by, and the top is 0 always if z is equal to 3. So I'm ignoring that. I'm doing comma, z equals 3. Because if you think about it, no matter what t is, z is always equal to 3. The z component is locked down. So here's the symmetric version of a line, that sort of special case when one of the direction components is 0. It's just a weird little pitfall. that I pointed out. Anyway, three ways to write a line: vector, parametric, and symmetric, and you should know how to go from one form to the other form. They're all basically three different ways of expressing a line. They're three different ways of giving you two pieces of information. What's a point on the line? What's the direction vector of a line? All right. What about intersection of lines? Now in 2D, lines are either, so if can I do this? I'm trying to erase all this stuff. Okay, the payoff will be bad because I'm going to go, here I am in 2D, and in 2D, lines are either parallel or they're not. Okay, so all that erasing, yeah, and that was what you were waiting for. So how can I tell if lines are parallel? Well, they have the same slope. If they're written as vector equations or or symmetric or any one of those three forms, if their lines are parallel, then I'm talking about 2D. If the lines are parallel, then their direction vectors are also parallel. If their direction vectors are not parallel, then the lines must intersect. They must cross because the lines are not parallel. But things get more difficult, or we got to think about it a little bit more clearly in 3D. Because in 3D, we can have, I'm getting my pens and markers out and stuff. Here's lines lie in 3 space. They could be parallel lines and not cross. How can I tell if they're parallel lines? Well, they should have parallel direction vectors even in 3D. They could cross, so if the lines cross, their direction vectors are not parallel and they intersect. But you could also have lines that are not parallel but don't cross. Those are called skew lines. One just passes over the other one. In 3D we can have that. In 2D we can't have that. In 4D and 5D and 8D we can also have skew lines. In 2D the lines are parallel or they intersect, and that's all the choices we have. All right, so I understand then in R3 and R4 that we can have parallel lines, intersecting lines, or skew lines. I can tell if lines are parallel or not by seeing if their direction vectors are parallel or not. Here's 2 lines. So the first one is written, the first one's written as in vector form, but I can still see there's the point and there's the vector. It looks like a point. I should really put, because I want to add a vector to a vector, I should use for the point that it goes through, 1, 1, 2, I should probably use the vector notation to be really good. But I can see that this first line goes through the point 1, 1, 2 and has direction vector 1, 0, 9. This second line is written in parametric form, but I can still see the pieces. It goes through the point 2, 0, 11, and has direction vector 1, 1/3, 6. So first off, do these lines intersect? The first thing I can see is direction vector of one and the direction vector of the other one are not parallel. 1, 0, 9 vector is not a multiple of 1, 1/3, 6, so they're not parallel lines. So my choices are they intersect or they're skew lines. Well, if they intersect, then there must be a point that's on both lines, the intersection point. So I know that I'm going to turn this first line into parametric form. So the x component would be equal to 1 plus 1 times I don't want to use the same. I don't want to use the same variable, the same parameter. It's written t and t here. I'm switching this to k because this value of t doesn't have to be the same value as t here. So I'm switching it to k. So 1 times k is the x component. The y component of this first line is equal to 1 plus k, and the z component of this first line is equal to 2 plus 2k. So now I've got the both lines written in parametric form. If they intersect, then there must be a point, an xyz point, that's equal to the xyz point on the other line. So this should equal to 2 plus equal to t over 3 equal to 11 plus 6t. So now you see why I didn't want to use t and t, because then the t's would cancel out, but they're different. The parameter here could be different than the parameter here. Now I've got 3 equations. 3 equations, 2 unknowns. I got more equations than I need. So if I can find a t-k pair that solves all 3 equations, then the lines intersect. If I can't, if it's impossible, then there's skew lines. All right, let's solve these first equations. Oh, my bad here, right? This should be okay. Duh. This should be k times the point 1, 1, 2, the vector 1, 0, jump to here, 1, 0 times k, 9 times k. All right, well that's frustrating but this makes my math a lot easier, because the first equation has to be true. If the first equation is true, and by first I mean the middle equation, t has to be 3. If t is 3, then this side is 5, so k has to be 4. So I solved for 2 equations, 2 unknowns, which I know I could do. That's like the intersecting lines in 2D. But now, does the t equal 3 and k equal 4 fit in the bottom equation? If it does, then I found a tk pair that solve both sets of equations so the lines intersect. If it doesn't, there's skew lines. If I make t equal to 3, this is equal to what? 29. If I make k equal to 4, this is equal to not that. So do they intersect? No. This solution, this last equation isn't satisfied by the 4, 3, k, t pair. Last thing to do with lines. What about a line segment? Now, lines are supposed to go on forever in one direction and forever in the other direction. A line segment starts one place and ends at another place. So let's go back to our example where we got the equation of a line that goes through 2 points here. And let's switch it for find the equation of a line segment. That joins those 2 points. Well, it's actually pretty straightforward. If I wanted to start at if I wanted to only go to the point 1, 0, 2, I would make, so I'm going to make L for line segment. I would just go from the origin to the point with that vector. If I wanted to go to this point 910, I could go straight there, but what I want to do instead is I want to go to this point and then go first and then go along the direction vector and end up at this point. So I need the direction vector that joins those 2 points again. So the direction vector that joins those 2 points is, we had that before, it was going to be 8, 1, minus 2. All right, this is exactly what I typed up there, except that I'm going to make k go from 0 to 1. Now it's a line segment. So if k is equal to 0, I'm at the beginning of the segment. If k is equal to 1, it's this point plus 1 vector that takes me from here to here, so I end up at the point 910. If k is a half, I'm halfway in between those 2 points. So making a line segment is just like making well, it's this point plus, or another way, if you want to think of it as a weighted average of the 2 vectors, another way to do it, so this is the answer to the question. That is the line segment. But another way to do it. So, or you could take the 2 vectors and take a weighted average. So let's take t times the first and 1 minus t times the other. It's still a one-dimensional object because there's only one parameter t. But if I made t a half, that'd be half of that vector plus half of that vector. If I made t, 0.8, be 80% of this one, it would be closer to the point 102. If I simplified this, it would simplify into the same line. They're both the same line. Anyway, line segment.